thing, and it should all now be perfectly seamless. Okay, here we are, folks. I was just checking back on WhatsApp, actually seeing where we are in time. We're on track. Chapter 9, Chapter 10, Chapter 11. That's what's left still. I was slightly musing. I was trying to do two chapters today. Let's see what happens. I'm going to start with Chapter 9 and work through these slides. This stuff starts to get a bit more familiar to you into the things you realise. This is what Chapter 9 is about. Transport layer protocols, what they are, how they support communications, the characteristics of specifically TCP and UDP, port numbers and their uses, how they operate in supporting end-to-end communications. So we're going to just really look at comparing and contrasting TCP and UDP. These are two protocols for the transport layer that you use for different things. It's all going to make sense now. There we go. So the transport layer, if you remember back to your... Oh my god, and my face is in the way of this. Can I move this? No. Move. Oh, why? There's going to be this in the way. Oh, please. I'll think about a way of doing that in the future. Anyway, see here, this diagram. Remember the old OSI model? Transport layer sits between the internet layer and the application layer. So what this does is it allows a temporary communication session to be made up between two applications and allow data to go between them. You can see here they're just really moving things backwards and forwards. Like, think about it. You've got an internet connection, you've got data flowing on it, you've got loads of apps open. On average, let's say you guys typically at home on the internet, maybe doing Cisco stuff, how many browser windows have you got open?
32 on mine.
Yeah, you maxed it out.
Terrible, yeah.
That's good, so you're a multi-tasker. And then, so what else might you have on also running at the same time in the background?
A spreadsheet.
Like an Excel, anything else which is internet connected?
Oh, sorry, Skype.
Okay, you might have some sort of a messenger open, like Skype. Okay, you might have Facebook Messenger open. Maybe you've got, some of you might listen to streamed music when you're doing other stuff, yeah, in the background. There might be a video chattering away in the background, so it's always more and more, isn't it? So the idea is that, if you think about it, lots of applications running at the same time, one internet connection, how are we going to be able to handle all the data for all the applications in some seamless way? So when Mark clicks on Skype, it works just as well. All the browser windows open that are doing things as well. The music's still streaming all the time as well. That's all being handled. This is done through what we call sessions. Okay, and the transport layer creates sessions between applications and the internet layer, and allows that flow of traffic backwards and forwards. So what we're doing is, we are an example on the screen here of things people are doing at once. So you've got multiple web pages, instant messaging, online video chatting, streaming video, and also a example of an email going forwards too. Tracking the conversation. We track each individual conversation flowing between a source and destination application. Segmentation. We can split up data into little chunks. Makes it much easier to manage and transport it. The header of a chunk is used for reassembly. So imagine each chunk of data has a header on it with some information. We can use that header cleverly to reassemble the data bits sort of in one effective larger block of stuff that's meaningful. Also, we need to identify the application. So even with many applications running on the device, all apps receive the correct data via something we call port numbers. So this segmentation, we call this multiplexing. We chop stuff into smaller chunks. This allows many communications to be multiplexed on the same network. Transport layer reliability. Two protocols. One's called Transmission Control Protocol, that's TCP. That's the biggest, most commonly used protocol on internet type work. The applications that work with TCP, FTP, File Transfer Protocol. HTTP, every day you use that for website access. SMTP is your email. Also something called DNS, which is Domain Name Services. You can see here how this is structured, this diagram. You've got your network access below there. God knows what's behind my head. Something. And what's this on your screen? Adrian, help me. One connection, okay. Internet is the IP, which is your protocol managing those connections. And there you go. TCP is reliable and ensures all of the data arrives at destination. As a result of this, we have some additional fields in the header that do increase the size and delay of the movement of TCP. The other side of it is using something called user datagram protocol, it's UDP. That does not have reliability. Fewer fields, but it's much faster than TCP. So given you've got all these different types of application I showed on the screen earlier, what do you think we might use UDP for?
Skype.
What kind of stuff on Skype?
Voice with ID.
Cool. Smart.
Calling somebody.
How did you know that? Common sense?
No.
Or just knowledge?
Anyway,
You ready before?
yeah, the thing is like when you're calling somebody, you don't really want to receive like acknowledge of the same. Okay, it's a frame of the voice was missing. You don't want to receive it again, like echo again.
Great. It's very good. Well done.
Live streaming.
Live streaming is great as well, UDP. The reason why, as you've correctly said, if you drop a frame or a packet in a live stream or a sound stream, it's not so much of a big deal. You know, it just carries on going. Like you might get some chunky frames or some really blocky graphics for a bit, and it just becomes really low quality for a little while, then it improves again, right? So it's okay, it still works, right? That's UDP's job. It's handling that kind of stuff. But stuff that is like, you know, mission critical, like email, you know, TCP handles those sorts of things. Or a web page, you're trying to hit a web page, you want some information, it'll hit that and it'll give it back to you. It's a little bit slower, TCP. It has this header on it, which is the reason why it's a little bit slower too. And the size is also larger too for TCP chunks. Okay, that's the big contrast between these two protocols. TCP transport is similar to sending tracked packages. So think about DHL, FedEx, these kind of couriers, okay? If a shipping order is broken up into several packages, a customer can check online to see the order of the delivery. You go to Amazon, you buy 5 things, different days of the week. They come back to you, they come different delivery dates, you can still track each one of them individually, right? It's much easier to manage it. TCP is able to do this concept. So this example here, this guy's sending a file across. There are 6 segments of it, and they're going over through this complex situation here. It's just a file going over. And the first 3 out of 6 segments are forwarded to the server. So split them up and send them over. Then what happens? The file server says, I've got the first 3 received well, and then the client sends the next 3 across as well. Okay, so it carries that across until they're all completed. If no segments are received, nothing at all, no acknowledgement is sent back. Because if something's failed, like the first 3 didn't get there, there's no acknowledgement saying send me more. Okay, so only will send stuff further if it's working down that line. So 3 responsibilities of TCP: numbering and tracking data segments, acknowledging received data, and if there's a certain period of time that it hasn't happened and you've got no acknowledgement back, it will retransmit any acknowledged data after a certain period of time. UDP is for less overhead and to reduce delays, so this is called best effort delivery, unreliable. No acknowledgement at all. It's a bit like a non-registered letter going out in the post. You send a letter, you hope it gets there. You have no idea what's happened to it. Yeah? Here's an example here of a file being sent across best effort and it's reached. All the files have arrived actually, but no acknowledgement was sent and nor was it needed. Okay, so moving on. The right transport layer is used for the right application. So we talked about TCP. Databases, web browsers and email clients require all data that is sent arrives in its condition that it was sent in. The quality is there. UDP, if there's a slight failure on a segment of a live stream, doesn't really be noticeable to the user. So you've got some kind of like just differences there between the two of them. And you can see the kind of contrast of the stuff here and that one there. TCP features establishing, so this is the sequence of, or we can say the hallmarks of TCP. This might come up in a multiple choice question, for example, in a theory test. You might say which one of these is a feature of TCP, for example. Establishing a session. The protocol is connection orientated. The application must be ready to receive. and it also negotiates the amount of traffic that can be forwarded at a given time. Reliable delivery, each segment arrives at destination. Same order delivery, because we can number and sequence the segments, like I can flag a segment up, I can call one A, B, C, D, E, different chunks of data. And like imagine that A, B, C, D, E, A, B, C, D, E, all being sent down different orders of letters going down the line, right? Then I can then what I can do is because I can get all the A's in a block, I can put all the B's in a block, all the C's in a block, and all the D's in a block, and push them into the right application so they get resequenced and reassembled in that order. So it's a bit like this. Imagine A1, B1, C1, D1, A2, B2, C2, D2, yeah, A3, B3, C3, D3. Then I'll take them apart. A1 plus A1, A1 plus A2 plus A3 is the whole of the A chunk. I can send it to the application A, whatever that is. Same for B, same for D. This is a quick logical way of sending things out. So we've got guaranteed reassembly. And finally, flow control. This is again the amount of data the source transmits. It's just being able to regulate that so it's not pushing too much down the line. That can be actually tolerated. If too much is coming down, we can't do the multiplexing so efficiently, you get more mess. It doesn't quite work. Oh my god, my screen just went. Oh, what happened? If it comes back, odd thing, my screen just went. Let me just check that out. Duplicate. Hey Adrian, my monitor cable, is it in alright? It's in power save mode. What odd. I better work with the screen, folks. Know what's happened there. What happened there, eh? It's just in power save mode. This is a new thing that's come up now. We're using Skype. I hope this all works, you know. Keep recording. Let's go back. Got to use this now. Where was I here, yeah? Oh, crikey. Just want to try one more time. There's no signal coming from your computer. Why would it do that? This cable's alright, yeah?
Yeah, no problem.
My side of it. How about the other end of it, your side? I must say, I did touch that cable very slightly at the bottom. We link both sides.
Both ends.
It's very strange. This is entering power save.
Where's that white one going to go?
The white one. I don't think I pulled that out of anything.
And it's from splitter, not splitter, but feature.
This one.
What was coming out of there? Is there a spare slot at the back of that line? Yeah. That sounded good. That sounded good. Well, hey, that did something. Well done, Adrian. It's all good now. It's cool. It's just one slight touch on it, it'll go funny again. I don't know what on earth it was. All right, let's move forward. Okay, so TCP header. This is what it looks like. Source and destination port used to identify application. So you've got your source and destination port there. Sequence number for reassembly. Acknowledgement number shows the data received and ready for the next byte. Header length, length of TCP segment, control bits, purpose and function, window size, number of bytes we can take at a time. Checksum, this is an error checking system. This really counts up everything so far, puts a number on it and just checks that everything has been put through. You might be aware of the word checksum before. Programming speak. Okay, so that's the kind of idea of it. It's 31 bits there.
It's like a frame though, isn't it? It's a bit like a frame, isn't it?
It is just like a frame. It's very similar. A lot of the frame structure is similar to this stuff. This is just a TCP header. UDP features. Now onto this one. So we mentioned some of the features there. We reconstruct data in the order it's received. This is so basically it's first in, first out, and as it's received, you just deal with it as it's coming in. Any segments lost or not resent. No session establishment, and the sender is not informed about if the resource is available or not. It is called stateless, has no tracking. The application is handling the reliability, so Skype or whatever it is, if there's a problem, the application has to handle the problem. And this is a much smaller header, you see the size of it. Bit to end, source and destination, length and checksum, and then the application layer data at the bottom there. It's a much simplified segment than compared to TCP. So we do have multiple separate communications going on all the time. Users can expect to get an email, view websites, make a VoIP phone call. And this is done using something called port numbers, unique identifiers. So if you look down here, You see this email here, HTML and internet chat. Special port numbers allocated to these. A web page, for example, normally works on port 80. Email 110. These are just standard port numbers. Even like any application has a specified port number on some universal list of port numbers. Like Minecraft, when it was out there, yeah? Remember Minecraft, a little funny computer game? I remember looking through port numbers thinking, oh, look, Minecraft is on there. All the big games are on there too. They have a port number, yeah, because they're running an application off the internet. And Minecraft, well, that's on there as well. That was also having its own port number. I never played Minecraft, by the way, ever. Just thought I'd clear that up. Right. Looked like fun though. Source port. So here, this is the originating application port that is dynamically generated by sending device. So each conversation is tracked based on the source ports. Destination is where it's going. So, e.g., port 80 web services are being requested in this example here, in this line. These numbers are placed in the segment, these port numbers, there's 2 of them there. So here we're saying this IP address is going to that IP address, the port on the source is 21, destination's port is 1305. These are what these port numbers actually mean. So if this source is 21, it's a bit random this actually, going to destination 1305, it's simply just saying that these are the port numbers allocated in this instance to FTP web servers, client source and FTP client source here. I'll work out the order. This diagram seems a bit odd because the destination port is 21 and that's the source port, and then the client source is 1305, which is destination port. Wondering, is it re-arrowed the wrong way around? Something's a bit fishy with that. The way this port thing looks like is like this. You get an IP address, a colon, and then a port number. And we call these, like when these are paired up, we call these socket pairs. A socket is an IP and a port number together. That's a socket, like this. They enable multiple processes to be distinguished. And the source port is also like a return address. Something fails, this is where it's come from. We can work that out. Okay, the location of it there. There are some well-known groups of port numbers. 0 to 123 are the well-known ports. 1024 to 49,000 or so registered ports. There's also a set of private and dynamic ports. What are they used for? I mean, this second one here are assigned by the Internet Names Authority to use with specific processes or applications. The last one are assigned dynamically by the client's operating system, and they can work with various applications during communication. The top one is the well-known services and apps. Here's some examples. TCP, read some of these out to you. Like a telnet is 23, FTP is 20 or 21, domain name service is 53, hypertext transfer protocol HTTP is 80, and also secure HTTPS is 443. If you run Wireshark on your home computer on an Ethernet line or on your wireless, you point Wireshark at that capture point, you'll start seeing the port numbers appearing alongside it, and while you're running applications and doing stuff, it will start showing you the port numbers involved with it if you ever wanted to have a look. Okay, there's a command called a network utility that you can use to verify what the port numbers are if you ever want to look them up. So at any point in time on a home PC, you can type in netstat, and it will show you the current active connections. So by default, netstat will attempt to resolve IP addresses to domain names and port numbers to well-known applications. So it will try and work out the domain, like here, see here, cisco.com and Microsoft here. It will try and work those out when it can do. -n, the option, if you put netstat space -n, this will give you the display IPs and ports in numerical form only, just IP addresses. Okay, so without it, you get the domain name resolution where it's available, and with -n, you get the detailed IP addressing. 9.2. Okay, so these are now some of the processes involved. So TCP server process. Here's an example of client sending some requests. Client 1 is making a request. Source 49, it's really tiny, sorry folks, you need to look at this on your PowerPoint if you want to see it. I can't zoom this actually. So look at you took your PowerPoint on in Moodle. I put it in there. I'll look at this. I'll just read it out to you. So this source 49152 and destination port 80. What this is doing is it's asking for a web page. Okay, it's making a HTTP request. That's a web page request. It's going to this server here. This has HTTP on port 80, which is where this destination is set to. SMT port 25. So in this example here, these are well-known port names. 80 is always one used for web pages, so it's just putting that down from the server. This email is destination port 25, which SMTP is configured 25 there. Okay, the source port on both of these are used again by the operating system, dynamically allocated. Yeah, remember that range I showed you? There was a range, yeah? The higher, above 49,151. Above that is the range where you can allocate a source port. The OS is doing that. Showing you that here. Both dynamic sources are being highlighted in this diagram here. Okay, does that make sense, folks? So far? Ask me a question if not. Feel free to fire a question in. Okay. So on the response side, when you've made that request, it reverses things around. So what happens here is the server response has to have a destination and a source. The source of a server is where originally it came from. This web browser here has, sorry, this web server has a port 80 for web and SMTP 25. This is just pushing down. Both sources are the same as what the server has, but the destination port is now the opposite of what the source port was before. Yeah, the source port, for example, was 49152 because it knows this. When the request came to the server goes, this came from 49152. That's when you send it back to this port. Yeah, it's just a way of communication backwards and forwards. So that's what's happening in both those examples there. They are responding to the request to the client. The server is issuing back a response with information. Okay, now TCP connection establishment. There are some steps involved with TCP connection. When I see this kind of diagram here, this is what you might get again in a theory test. This is how it looks. A theory test might show you a diagram like this, and they might ask you to rearrange the order of what happens when. So you're going to kind of memorize how the sequence works. It is fairly logical. Step 1, initiating client requests a session with a server. Here's your A, there's your B, and this send SYN, okay, SYN here, is that request to the B over here. So SYN is sent and it is received at B. Okay, when it's received, what then happens is step 2, it acknowledges and requests a session with the client. So it sends back a SYN and also an ACK acknowledgement back to the A client. Step 3, the client acknowledges communication session with the server. So it bounces backwards. So when it comes to here, the client says, yeah, I'm ready to go. Give me what I need. Established. The session is then connected and open. So the sockets have paired up and they're able to communicate. Established section 3 there. Wish I could move this out of the way. Is there a way of me doing it? Mute. I might mute me actually. I don't want to mute myself. Okay, moving on. Session termination. When the session's complete and done its thing, we have to also terminate the session using this command. The client sends FIN to B, and B has then received it. Okay, once the FIN is received, it then sends acknowledgement back to this source. Okay, the ACK is received. Look, it's so like over complicated in a way. Like, what's going on here? ACK received. Then something else is sent. Sorry, the acknowledgement is sent to A. Then the FIN is sent to A, saying I have now completed my stuff. Okay, session finished, FIN received. And then after all of that, A then again says acknowledgement. Yeah, we're all finished, done. ACK received. Job done. Okay, so the FIN must be set in the segment header. It's a control flag. This is called two-way handshaking, using both FINs and acknowledgements. Okay, we must have this full loop completed to terminate a conversation to end both sessions. Because you're going to end the session not only on the client side, you're going to end it on the server side too. Okay, so the conversation's over at that point.
So does the client send a FIN to the server?
You can see here, the client's never sending a FIN. The client's just saying, yeah, I'm ready to receive the FIN.
Oh.
Yeah.
Oh,
Apologies, towards the end. I mean, it starts off with the client, sorry, it starts off with the client sending a FIN. That's initiating, but then the server is the one that closes down the fin.
Oh yeah, that's right. Yeah.
Yeah, it starts with the fin, and then the fin goes back. That's right. Okay. See, confusing or what?
It is a bit.
Okay. TCP, three-way handshake analysis. Okay, here we go. The three-way handshake. This establishes a destination device is present on the network. It verifies it has an active service. Remember, this is TCP, okay? This is like requires fault tolerance, you know, to be able to handle errors. So it verifies destination is active and accepting requests on the port number the initiating client intends to use. It informs the destination device the source client intends to establish a communication session on that port number. The 6 bits on the control bits field here, 6, are known as flags, and there are various flags that are used to reset the connection when an error or timeout occurs. I'll read the flags out to you. One is URG, urgent pointer field significant. One is ACK, acknowledgement. PSH, push. RST, reset. SYN, synchronize. Sequence numbers. FIN, no more data from the sender. Not going to go through this. So there's a little video here that it's got of Wireshark being used, showing the SYNs and ACKs in motion and what's actually happening there. That's something you could watch. The labs they've allocated here are all Wireshark labs of you looking at your own home PC and what it's doing when you do multiple things. Okay, that's something you can try out. This is not a part of the exam, by the way, or skills assessment. It's just something to understand what's happening here. Sequence numbers. So let's talk about this next. Sequence numbers are assigned in the header of each packet. They represent the first data byte of the TCP segment. During the session setup, the ISN, initial sequence number, is set, representing the starting value of bytes. As data get transmitted, the sequence number is incremented by the number of bytes that have been transmitted. Therefore, we can identify missing segments. So say here, these segments can bounce around various routes to get somewhere, okay? They could go through different routers as well. So to get here, we've sent them across in 6 chunks. They've all arrived in different order. Look at this, they came 1, 2, 3, 4, 5, 6. They arrived 1, 2, 6, 5, 4, 3. What TCP does, it goes, all right, let's just reorder this before we get you into the application. So it just reorders that number because they could arrive at different timings, taking different routes to get there. This little video here in Cisco Academy shows you this sequence numbering and acknowledgements and how it's working. Also happens in data loss and transmission. Okay, onto TCP flow control, window size acknowledgements. So in this example here, source is giving 1460 bytes of data within each segment. The window size is agreed at 14360 during the three-way handshake. PCB will not wait for 10,000 bytes before sending acknowledgement. In this example, PTA can adjust its send window as it receives acknowledgements from PCB. So here we can see A to B. Send window size 10,000. That's what agreed on the handshake. MSS is like kind of a minimum sort of size frame. So it sends across the first sequence 1460, all received. Then it sends another chunk, all received. Then it receives an acknowledgement saying, yeah, I got that back. Acknowledgement 2921 received. Window size still 10,000. Okay. Another one comes through, another 1460, then another acknowledgement comes back. Okay, that's an example of how window size is used to chunk data, send it backwards and forwards. So, biggest problem is with TCP, what can go wrong, is we get network congestion. If that happens, we have to retransmit lost TCP segments. Okay, when they're getting retransmitted, it can make the congestion even worse. So to avoid that kind of real bottleneck of stuff, TCP has some congestion handling tactics, yeah? Timers and algorithms. And one example is reduced number of data it sends before getting acknowledgement. It just reduces that size, that window. Rather than having it say 3,000 or 7,000, if I made it much smaller, like maybe a few hundred, I've got a better chance of working out exactly what's missing. The bits that are also not allocated, and also it avoids the congestion of So much stuff being put down the pipe. In this example here, there are 4 segments being sent. 2 and 3 fail. I'm acknowledging I've got 1. This is a mistake, by the way. I've got 1 and I've got 4. There's 2 there. I've got 4. 2 and 3 have failed, right? So it sends 2 and 3 again. That's it. Just retransmits what's not read. Because this whole thing is, the whole idea is to manage the flow. Nothing gets dropped.
So what doesn't get acknowledged gets retransmitted.
Yeah, correct. It's almost like saying, it's like you sent me, it's like Mark sent me 4 letters. Mark, I got 1st and 4th, yeah? And I know I didn't get 2 and 3 because it says here, you know I haven't got 2 and 3. You're the sender, I'm the receiver. So I say to you, I respond back saying, I got 1, I got 4, 2 and 3, what happened? You go, oh, 2 and 3 is missing because you're on the receiving end of it, and then you will resend the 2 and 3 back again. And I'll acknowledge that after that. Then we know we're done, yeah? Okay. So reliability versus low overhead. Because UDP is not connection orientated, no retransmission, sequencing or flow control, functions not provided by the transport layer are implemented elsewhere. So it's to say this small datagram header, this is a video being sent across this network. No connection established before sending data across. UDP reassembles data in how it's received it and forwards it to the application, but the application's got to now handle the correct sequence. Okay, the application is now doing this. So you can see here again, datagram. Here's a video to video call. It's taking many different routes. It's all going out 1, 2, 3, 4, 5, 6, arriving in some jumbled order 1, 2, 6, 5, 4. It is not requesting one that's missing, which is 3. It's just, and it's not even reordering it. So it's just jumbling stuff up. That's why you get videos that go really weird sometimes, or sound files or audio on like Skype call. Or that kind of audio call, it goes all buffered and it goes a bit clunky, you know. You kind of lose the sound, or you get a word later and one word before, it just gets scrambled in some way. This is datagrams. No assembly, no, it just as out as it receives. So imagine it could go down like 5 different routes, this data. All these routes are bouncing around, it all has different distances. So it might go that way, it might go that way, it might go that way, that way, that way, that way. Therefore, they're going to arrive at the same time. Yeah. So therefore they're not going to be, but they're also not reassembled. But the application, depending on how complex the application is or how sophisticated, it can work out and reorder stuff. The application's job is to do that. Okay? But they're not reordered as such. The application's handling it inside itself. Okay, some examples of this is an example of a request. Remote authentication dialing user service server. This provides what we call AAA services. AAA stands for authentication, authorization, and accounting to manage user access. So it's just saying here that this particular client 2 and client 1, this server is able to receive requests on port 53 for DNS and port 1812 for radius requests. This is like user service server. It's like a remote dial-in thing here. Okay, that can connect you into the network. So what's happening here is, as those requests work, client requests the UDP server to use well-known port numbers. So it's just simply, as you can see here, using a source port. It's allocating a source port on dynamic fly here, and using well-known port numbers for DNS and radius 53 and 1812 to make those requests and get the things back. Yeah, but random numbers are used for the source ports. Again, the OS is allocating those. Destination is reversing this, so sending stuff back using the same port numbers. Okay, let's explain that. Repeating that thing again, really, there. This again is a little Wireshark. It shows you a UDP DNS capture. Applications that use TCP, things that are well known. So you would have heard of FTP, TCP of course, HTTP, SMTP and Telnet. And TCP, what this TCP layer is doing is, it's freeing the applications from having to manage reliability for TCP. And in UDP you don't have that problem. The applications are having to manage reliability. Okay, but TCP is taking care of it in terms of that type of data. So the best things for UDP are live video and multimedia, simple request and reply, and the handling reliability themselves. So you can see here IPTV, VoIP, TFTP, it's another special type of file transfer protocol. DHCP, which is allocating of IP addresses, SNMP, and DNS are the protocols there.
But I thought TFTP is actually like a server. You can request it up. It's like a.
Yeah, it is it's like a FTP server. It's like a file. It's like a type of FTP which you set up on a server, but it has some different properties than normal FTP does. FTP has this connection properties of making sure you reach that destination, you know, and you put something there, like you make the session, then you put things there, and it's all acknowledged and received. Yeah, and it's also done in the right order. So if I send it this chunk of stuff, it reassembles it properly. Whereas TFTP, it just first in, first out. Like it goes in, and it arrives. You know, hopefully. And if there's a drop, it's a drop. You know, you get a corruption.
When I tried this one update my switch recently, it was going through TFTP, and I thought it's like a TCP, you know, like it's acknowledging and getting everything back. So it's just the best effort, like.
Well, you see,
it's
UDP is the protocol managing it. So if it's UDP, the application running that TFTP, the application side of it is handling all the unreliability that's going on, whatever that application is. You'll come across TFTP in your skills assessment. That was mentioned there as well. Okay, using Wireshark, another Wireshark capture. This is basically just like Wireshark. You basically send Wireshark and you watch what's going on. That's the chapter done. There's one packet tracer in here, activity, you know, which is, we could look at that one actually. Do you think we should look at that packet tracer activity, folks? You up for that? Yeah, we should do it. So let's do something practical now. I'll get the packet tracer activity out. What's the number of that code one, folks? Come and read it out to me.
9312.
9312. Let me get hold of it for you. We'll do that now until break. Yeah, and then we'll see after break how we're doing. Okay, cool. Let me just see if I can stop this recording.